Now I will use the big theta and big O notation to go through the insertion sort algorithm to analyze its running time. Okay, so this is the pseudocode we have already implemented, and just recall the way that we analyzed the running time previously in the getting started lecture. And we assume that each line of the code, to execute each line of the code for once, will cost us constant amount of time. And then we need to count how many times that each line has been executed. So if the input is of size n, then the first line has been executed for n times, the second line has been executed for n minus 1 times, and so on. Okay, and particularly for the TJs here, it is TJ because we don't know how many times the while loop has been executed in the J iteration of the outer for loop. So that's why we have these unknown variables here. Anyway, given these two columns, we're able to compute the total running time T of n as the summation of a bunch of products. Okay, so simplifying this long equation, we can consider two cases. In the best case, TJ is 1, right? So for that means the while loop has been just being executed for once, and there's no swap needed between the key and the element before it. So in this case, T of n turns out to be a linear function. Okay, and in the linear function, then we can apply the big theta notation to say that T of n is the big theta of n. And in the worst case, the key element needs to be compared with all the values before it. So in that case, Tj is j for each j. So in that case, the T of n turns out to be a quadratic function. Okay, so a quadratic function, we can basically write it as a big theta of n squared. That's what we know from this lecture, right? So altogether, however, we can combine the worst case and the best case. So the worst case can be the upper bound, and the best case can be the lower bound of the running time. Okay, so altogether we can say that the T of n can be described by the big O of n squared and the big omega of n, right? So because the lower bound is not big omega of n squared, right? Because in the best case, when the input is already sorted, the running time can be linear time. So the quadratic running time is not the best case, is not the lower bound. So in this case, we cannot use big theta of n squared to describe the running time of insertion sorts. Okay. So that's an example showing how the big theta, big omega notations, big O notations can be applied to a insertion sorts analysis.